Hi engineering students. I'm going to come to you today live from our campus. I just want to connect with you a little bit in person. We are nearing the end of the first quarter. We have this long unit that I've called forces, moments and vectors, and I just want to talk a little bit through that. I want to give you a little bit of hope in the long slog, because everything that you've been doing so far this year is just about learning the vocabulary of how things move and work and fit together. Okay? You cannot write an essay on the history of economics if you don't first learn the basic terms. You know what words like markets and interest and supply and demand mean. So after you learn all these things, after you learn the vocabulary, then you can actually use that vocabulary to do meaningful things. I want you guys to know what it takes to be able to calculate the force necessary for a rocket to take off. I want you to know how many screws are necessary to hold a building together. Okay, we're going to build that furniture for our two clients, and you'll need to understand, what does it take, how many things. So we're giving you all that vocabulary, which sometimes can be a little bit tedious, and I understand that. My ultimate hope is that you would be able to have the superpower of being aware of the whole world around you in physical, measurable terms. So when I look at an object like this tent that we just installed today, and we're going to set up a few more of these to create some shaded area here on the green space. You guys are the first ones to see this. When I see that tent and I see the 6 legs that it has, okay, I kind of have this superpower, all right, of being aware of that, and I see it, and I see the force vectors distributed, divided by 6, and laid out on each of those feet. All right. When I see the cars over there in the parking lot, I see like that weight vector, and then it's bang, 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 bang on the 4 wheels, and as that car moves and as it brakes, I see the force shift to the front wheels and like kind of lift up on the back wheels. It's a little bit, it's kind of like that augmented reality Tony Stark Iron Man suit kind of thing, and that's what I want to give to you. But it takes a lot of practice and training to get there, and it takes some math, and it takes some physics, and it takes some study and some reading. I want you to be able to walk up to a door and understand that when you pull in that door, if you pull with a very perpendicular force, that you get a much better amount of moment than if you say kind of like pull outwards to the side this way. You don't get the same perpendicular effective moment, and that's the kind of stuff that we're talking about right now. So you will walk through some of this and you'll stumble through some of it. For the younger students especially, this is going to feel like a bit of a slog, but you will get your license to be flying with Tony Stark's Iron Man suit before long. I just saw on Sunday, I met with one of our recent graduates, and she's at Embry-Riddle Aeronautical University, and she's saying how the stuff they're doing there right now, man, she was doing it in middle school back here at Providence in the engineering elective. The stuff that I taught in 10th, 11th, 12th grade, that's what's happening in sophomore level engineering up at Westmont with another one of our alumni. I was just talking about this today. So I'm giving you guys the equipment to have that Tony Stark augmented reality that you can then use to bless people, to put things together, to do stuff, to design things. So stay strong. We're going to zip on back. We're going to finish our discussion of moments and how they work. And I just want to say, you guys are doing a fantastic job. Do not lose heart. Keep it up. And I hope that we're back on campus again very soon. Bye. Okay, so let's go back to the studio and we're going to look a little bit more about some moments and how they work. I think things are overall pretty simple when it comes to moments. We've talked about this already, but this here, and if you want to get into the vectors as well, you can do that. But you know what, let's keep this as simple as possible. A moment is simply a force times a distance, and we're referring specifically to a perpendicular relationship between those two. That's it. That's the whole of the lecture from this first week summarized. Unfortunately, even though that is true, moments don't often come at you like that in the real world, where there's like one force, one distance, they're already perpendicular, just multiply two numbers. Okay, it'd be nice, but it's not always like that. So we're going to do two things today. We're going to do the more complex situation of where you have to add together multiple moments. And then the other thing we're going to do is we're going to say what happens, not adding, but what happens when you have moments, how can I say this, without perpendicular forces. Like what happens when the force is not perpendicular to the distance back to your axis of rotation. So these two things I'm listing here, they happen all the time. That's just like real life, that's messy life. And the whole idea is that you sort of take these things and then you convert them back to run through this very, very simple process. All right, let's get into the first one. Adding together moments. Let's keep this going, okay. Adding together. So the first thing that you must absolutely do when you want to add together some moments is you have to come up with a consistent sign convention. Please put this phrase in your notes. I don't know why, for some reason this year I haven't really majored on using that phrase. In years past I have. I should really swing back to it. The term sign convention, it just simply means it's when you say like what's positive direction, what's negative direction. Okay, we did this already when I said earlier this year, I said like draw a little picture like this somewhere, where like this is your positive x, this is your positive y. Or draw a little picture like this, where this is I and this is j. Anything like that is a sign convention where you define what is positive and what is negative for your different things. Okay, forget those, that's for forces. We're doing moments. So it's actually as simple as this. The standard sign convention for moments is that clockwise, CW for clockwise, is positive. That's it. All you got to remember is that clockwise is positive, which implies, of course, that counterclockwise, or anti-clockwise, as we say in Australia, is negative. But you don't really have to remember the other one. The other one is just necessarily true. The one that you just should really focus on, clockwise, is positive. Okay? And that kind of makes sense. We normally say clockwise before we say the word anti-clockwise or counterclockwise. And we normally say the word positive before we say the word negative. So it's not too hard to remember typically. So the way that we use this is think of like a seesaw situation. And there is a situation like this on your quiz this week. I talked about a seesaw in the first video, but this one's going to be a slightly more realistic seesaw. We're going to say we have a child that weighs 300 newtons, which is about 30 kilograms of mass. And, this is what we said in the first video, but kids don't normally play on seesaws by themselves unless they're kind of lonely and sad and have no friends. So we're going to put another kid on the seesaw, a bigger kid, older perhaps, who has 500 newtons of weight. And we're going to lay some distances out. We're going to say, all right, first kid is at 2 meters of distance. And you know what? Let's make it simple. They're both they're both 2 meters. We have our point of rotation in the green. And this time, the real critical thing that we're going to start to draw attention to is this fact that positive moments are the clockwise ones, and vice versa. So, I'm going to do it like this. I'm going to say sigma m. Now, you know what that means because we've been doing this all year long. If that is the one thing you take away, that is a victory. Sigma means sum, the sum of all moments. Then you do a little equal sign, and then you start to list them off. So the first moment is going to be this 300 Newton force times this 2 meter distance. And I'll do 300 times 2 because we know, right, that moments are force times distance when those are perpendicular. And then we've got to ask ourselves, this 300 Newton child, which direction is that moment trying to spin the object? Is it trying to spin it clockwise or counterclockwise? So, you know, it's hard to do this without standing in front of you and waving my arms, but I hope you can tell that this kid is, it's like pushing the seesaw that way. You can imagine the seesaw like tipping down and to the right. That would be a clockwise motion around that green pin point in the middle. Okay, that's a clockwise action that the 300 Newton child is doing. So because we said already that clockwise is positive, we're going to keep that as a positive moment contribution. Now there is a second moment happening. We also have a kid who weighs 500, also at a distance of 2 meters. Okay, force times distance, 500 times 2. So we're going to put that into the moment sum, into the sigma sum as well. And I know you know what I'm about to say. This kid is kind of trying to bend the seesaw back that way. That would be like a down and to the left thing. Okay. Now both these happen at the same time. We're not necessarily talking about what actually happens to the seesaw. That calculation comes later. We're just really talking about the tendency. Like, what's the tendency that this particular moment is trying to do, whether or not it will actually do it. Because there may be other things involved. Maybe the seesaw is like rusted, stiff and solid and doesn't actually rotate. The moments would still be there even if there is a resistance from the center. It just means that that hinge pin is creating a moment itself, a moment of resistance. But the 500 Newton kid is creating a, like, see this one here? It's like a counterclockwise action, which is negative. All right, counterclockwise is always negative in moments. So we're going to use a minus in front of that one. You know, maybe I should have, look at this, I've got this lovely color scheme happening here. Lovely and consistent. Okay, great, let's stick with that. And then we just calculate it like we would any algebraic sum. 300 times 2 is 600. 500 times 2 is 1,000. 600 minus 1,000 equals negative 400, and that is measured in Newton meters because we are clearly in the SI system. And what this also means is because you see this negative right here in your answer, the negative 400, you refer back to the fact that you know, because you set it up at the start, that negative moments are counterclockwise. So this tells us, this is one indication, if it wasn't obvious, that the 500 Newton kid wins the day and the seesaw tips counterclockwise in the way that we're looking at it. You can kind of tell that. It's pretty obvious. Bigger kid, smaller kid, big kid wins. It could get more complex. So what if the kids were at different lengths? What if, yeah, that would not make it necessarily quite so obvious because both the length and the force contribute. Here's another way this could work. I think I'm going to try to see if I can actually copy this diagram. Save redrawing it. Great, let's do this. Copy. Problem now. Whoop. That was odd. Sorry guys, I'm trying to work out how to paste here. Hold on. 1 second. Oh, okay, we got it. I don't know if you could see that. I had to pull up my on-screen keyboard. Okay. There we go. Okay, let's slightly change the scenario now. Let's say that we have the same kids, except the 300 Newton kid is still at 2 meters and he tends to create a positive clockwise moment. The 500 Newton kid is still on the other side and he'll obviously create a negative counterclockwise moment. But let's just pretend that we don't know what the distance is, or a better way to say it is that the distance is variable. Okay, that we are able to make it whatever we want. So we'll call it x. This is x meters. Find x. There it is. We're still going to do something like this. We're still going to say, okay, sum of all moments equals, but let's pitch the problem a little differently. Let's say that instead of just simply adding up what's there and seeing what we get as an outcome, let's say that we want the outcome to be 0, because remember what this is all about. This is a statics course, and in statics the sum of all forces are 0, but let's add to that knowledge, the sum of all moments is also 0 in statics. Okay, forces and moments are 0 in statics because not only do things not accelerate linearly, they also don't have rotational acceleration. Now, after we do this sum of all moments, sigma m equals 0, we still put together our moment contributions. We had, remember, a positive 300 times 2, because it was clockwise, okay, clockwise. And then we also had a negative contribution, but this time, because we don't know the distance, it's 500 times x for our counterclockwise or anti-clockwise moment. Okay, only change here, you can see that. The only change is instead of putting in a 2 for the 500 distance, I put in an x, and I'm making the whole thing equal to 0. I'm kind of saying to myself, how can we balance this? How can we make it so that the moments are equal to 0? All right, let's solve this. This is an algebraic equation. 0 equals 600 minus 500x. Now, I don't care what level of math you're at, that kind of thing jumps off the page, begs to be solved. You need to subtract 600 from both sides. You need to divide both sides by negative 500. And then if we simplify that, we end up with 6/5, okay? The negatives cancel, the 2 zeros on top and bottom cancel. 6/5, which by the way is 1.2. So what is the significance of that 1.2? What is that telling us? That is telling us that if you want to balance, if you want to make the moments equal to 0, if you want this thing to balance, you had better seat the 500 Newton kid at a distance of 1.2 meters. And then it will be a static situation. Then it will be balanced. All right, so that is a really, really common way that we use moments to find out what would it take to balance. That is how we do moment sums. Okay, I said this is like the first of two potentially messy situations with moments. First of all, how do you add them? So there you go. That was 15 minutes. How to add moments. Okay. The next thing is what happens when you have moments without perpendicular forces. Let's kind of keep working over here. What happens, and this is actually the example in the textbook, the one on the reading for this video. I think it's 3 pages that I gave to you. It's unfortunately a little bit of a complex one. It does involve adding moments as well as what I'm about to show you. It's kind of both of these two things put together. But let me give you like a more basic one. The basic idea is that if you have, let's put together all those different bits and pieces. We have an axis of rotation, just like last week. We have that same distance vector, okay, which by the way is exactly what we're doing over here. 2 meters or 1.2 meters, those were the distances, distance vectors. But notice in this one, see what happened here? I do not have perpendicularity. There's a good mouthful for you. In fact, a word that we sometimes use is oblique. Okay, kind of a French sounding word with a Q-U-E, oblique. That's just something which is not at like a nice clean right angle. So maybe, I don't know, maybe it's like 30 degrees. It's a good favorite angle because we can often use our brain knowledge instead of a calculator to do 30-degree angles. What do you do in this case? So the basic idea here is that you need to break down an oblique angle, a non-perpendicular angle. You need to break it down into its 2 components, and you have been doing that almost since week 1. Okay, that's why we give you that skill right at the start, because we use it in so many ways. So if you can picture this as a right angle triangle, I'm not going to show you anything new, just casting your mind back. There are 2 components to this vector. Okay, there is, in this case, it's not so much about there being like a vertical and horizontal vector, although in this case that I'm showing you here, that is what it is. It's more about that one of the components is perpendicular and the other component is parallel. Yeah, let me try it again. Give you a better version of that. Is parallel. That's just a little parallel symbol. Two parallel lines. Okay, a parallel component and a perpendicular component. But the process is completely the same. Let's see. Let's give some numbers here. Let's say this was 100 pounds. Let's use use US customary and mix it up. This long component, this perpendicular component, okay, this, you might recall, is 100 times cosine of 30. Okay, remember that if we do our famous magical SOHCAHTOA, that would be like the full version where you do sine of the angle equals opposite over hypotenuse and you work it through, you do cosine equals adjacent over hypotenuse, and you can also use tan equals opposite over adjacent. But if you work that through, you always end up, you might recall me saying this, that the shortcut, the simple one, Sam is going to love this, the shortcut is 100 times cosine of the angle, and then the shorter side is going to be 100 times sine of the angle. Okay, that's always what SOHCAHTOA will take you towards. And we can work those out. This one is going to be about 86.6, sorry, not degrees, forget that, pounds, sorry. This one is going to be 50 pounds. And I just know those from memory because we use them so often. But you can use a calculator to do that as well. Or if you know the square roots and things, please practice those as often as you can. I'd say 11th and 12th graders, you know what I'm talking about. So what you do is you break it into those two components. And then once you have a perpendicular and a parallel component, you pretty much say, forget you, parallel component, I don't need you. You only use the perpendicular components. Let me just again make up some numbers here. Let's say this is a 40-inch distance. So we will say our moment is force times distance, only caring about perpendicular relationships. So the force in this case is only the 86.6 pounds. The distance is the 40 inches, and do not ask me to work out what that is off the top of my head, but it's 3,464. And that is going to be measured in pound inches, because that was our units that were fed into it. Okay, 3,464. And you see what I did there. The original 100 pounds never ended up appearing in the moment calculation. Neither did the 50 pounds. The 100 got broken down to 50 and 86.6, and the 50 just can't produce any moments. In fact, if I were to draw this diagram a little more accurately, a little more helpfully, I could have taken, I'll take advantage of the fact we're using computer graphics. Really, oops, boy, no, I don't want that. Let's try this again. There we go. Come on. There we go. We're really taking that. That is a more accurate way to show where that force actually is landing, because even though it was helpful to draw the right angle triangle, because the point of application of that black original vector is right there where the arrowhead is, it's actually more accurate to show those two components as also acting at that one place. You might recall a little bit of the book about talking about like sliding vectors and things like that. That's kind of what I did just then, if you noticed that and were wondering. I haven't really mentioned it at all otherwise. Okay, it's the same length, it still is 50, but that's a slightly more accurate way to show where it actually points and lands and does its job. And so what you can see is that while the 86.61 is perpendicular and is able to, like turn this whole thing in a counterclockwise direction, that little 51 over there, okay, this little one here, that can't turn around the axis of rotation. I hope you can kind of imagine that. See where it's pointing? It's actually like pointing, its line of action is right through that axis. And I hope you can feel that at a gut level, that when you push with a force straight onto a hinge or a pin or some kind of rotating point, it doesn't rotate at all. You're like pushing right through it. It's like, imagine that you are, imagine like a bicycle wheel. If you grab the rim of the bicycle wheel and push on that, the wheel starts to turn. But there is a way that you can take that exact same force of pushing And if you point your pushing straight into the center of the hub and you do it perfectly, the wheel does not spin. You might slide your bike along. That can still be an acceleration vector, but it won't cause a moment because your line of action is right through the axis of rotation. It doesn't contribute. So I hope that all makes sense. That's what's happening here. Only the perpendicular part contributes. Let me give you another like a little physical example. I want you to see this a few different times. Okay, here's one. Imagine we are looking down at the top of a door. Okay, in the video that I opened with this week, this video that I opened with, I was walking around campus and I showed you, like the different ways you can pull on a door handle, just a quick little simple thing. So here you go, here's the door handle. We're looking down. Here, right here, is the axis of rotation, the hinge in this case. I'm standing here, here's the top of my head, and I'm reaching forward with my hand. There we go, that's my other shoulder. And here's the distance. And the distance on a door, look, that could be about 1 meter, pretty close to it. And as I say, I showed you like different ways I could grab that. So if, let's use blue. If I grab the door and I pull or I push, let's do a push. If I push with exactly 50 newtons and I truly have perpendicularity, then my moment is going to be 50 times 1 equals 50 Newton meters, with a standard sign convention of positive being clockwise. That would actually be, I should actually list that as being negative, shouldn't I? Because that is going to cause a rotation in the negative, in the anti-clockwise or counterclockwise direction. But what if we take away everything that I just said? What if we pulled a little differently? What if we pushed or pulled at a 45 degree angle? What happens then? Well, we would break it down, and let's see, I'll just use green. We can see the right angled triangle, just like that. And we can see that we have two components of the force. And sorry, I didn't give the value, did I? Okay, let's keep it as 50 newtons. So this component here is going to be 50 sine 45. This other component is going to be 50 cosine 45. Remember, with a 45 degree angle, you actually end up with the same number on both sides. This is what is this? An isosceles triangle, where two sides are the same, one side is different. And it's only one of these that I actually want, isn't it? In this case, they are both the same, but the moment is only going to be grabbing this one right here. So I'm only going to use this particular force times the distance. Now, what is 50 cosine 45, you might ask? Here, let's guess. I think it's close to 36. .4, we'll say 35. it's about 35. I did that on the calculator. And you know what, I'm going to put a negative the whole way through, because again, it is still doing a counterclockwise action. But notice it's a little less. If I compare between those two results, I got more oomph, I got more moment happening. I got a full 50 Newton meters when I pushed on the door in a perpendicular way. When I angled my hand and I pushed at a weird oblique angle, I only got 35 Newton meters of activity. In other words, 70%, okay? That number represents only 70% of the full 50 that I got earlier. And that's how it works. Like that's why when you pull on a door, you don't pull at oblique angles. You pull or push straight onto it. That's why when you're trying to turn a wrench on like a really tough bolt, you get fully behind it and you push with a perpendicular force. And that means every last pound or newton is being converted into a useful moment to do the job. Okay? This is a lot to do with like getting what they call a mechanical advantage, using your body in the right way, whether it be in sports or putting a car together or wrestling or whatever it might be. You can use the same forces in more or less effective ways because you can generate more or less moment depending on how you use those forces. All right, guys, I'm going to wrap it up there. I just showed you two complexities. I said this is how you can add together moments. This is how you can work out the moment when the force is not perpendicular. And I think that was good. I'm happy with where that landed. That was about half an hour of instruction there. Now, I'm going to throw in what I've been putting in the newsletter for the school and everything. It helps that your teacher is also the principal. I think there is a very good chance that we are going to go ahead with being back on campus next week. We've talked that through with you guys in the meetings. So yeah, it looks like it's going ahead, just judging by the county health numbers that we look at each and every day. So for next week, I am going to go easy on you in this class. I don't want to lose our rhythm too much, but I think I will give you a few days off. I'm going to give you a transition time. I'm hoping that a lot of your teachers take the same sorts of actions, not ceasing altogether, but going easy, because there's going to be enough to account for as it is with new rhythms, new schedules. After that little transition time of a few days break, I'm going to be putting you into teams, because you're all submitting your furniture concept models. I'm going to use that to determine which team to put you on. We'll see how many did each one, and we'll make teams that fit well. Very soon, like I'm talking like in a week or less, I'm going to have you start designing a more detailed model. But we first need to get these concepts, put them back in front of our clients and see what they say. Like, what do they like? What do they not like? You might have had some awesome ideas and they might say, oh, I love that. Like, let's go that direction. I wasn't thinking that earlier, but I love what you're doing here. And that's going to be really exciting. So we'll get their feedback, and then that will let us refine what we do. So at that point, it's kind of me stepping in and saying, all right, guys, we're going to narrow the focus. We're going to go with this feature, not that feature, and then we'll all pull together and design down that one path. Some of you who are keen on Onshape, as you should be, this will start to be a good time to do that. But I will give you the direction. So just hold off, wait, take those few days of break that I just promised you, and just keep an eye on Google Classroom. It's all going to keep coming through Google Classroom. You'll see the instructions there, and all will be well. All right. Thanks a lot. Good luck with the rest of your work. And more than ever, we will see you all soon.